So good morning and welcome to the COSIC seminar. It's a great honor and pleasure to introduce for this week Professor Bimal Roy. People from India, they all know Professor Bimal Roy. I don't have to introduce him. For those who are not from India, Professor Bimal Roy came here more than 25 years ago to visit me.
Yeah, 23 years ago.
And then I went to visit him back actually 1 month after 9/11. It was my most interesting trip ever. I was in 747s that were with 5 passengers, but you still were checked 5 times before you could enter the plane. But so since then, we've set up a very good collaboration. Professor Bimal Roy created the research group and program in ISI Kolkata, but he also became director of ISI, advisor to the Indian president and National Statistical Committee. And today we'll speak about his research with his last PhD student together. It's about secret sharing schemes.
Okay. Yes, thank you, Bert. So it's nice to be back to Leuven. I've been here quite a few times. I think last time I came just before the pandemic, and I gave a talk. And the first time I ended up here almost by an accident, year 2001. I needed some other reason to come to Holland, and I was rejected the Dutch visa. But that time, there was no Schengen, but there was the Benelux countries, Holland, Belgium, and Luxembourg. So I told Bert that, would you invite me? Then I can visit Holland, actually. And he did. And he said, it's not a fake invitation, it's a real. So I ended up coming here also. So that's how we started. And then I invited him to come to my institute. And that's so happened, it was around third week of September. And after the 9/11, I almost thought that he's not coming. And in fact, he says that, no, I'm coming. But I still didn't quite trust that he's actually coming because the flights were getting almost empty. I thought even the airlines might stop the flights, even if he wanted to come. But he finally ended up in Kolkata. And we gave a series of 4 or 5 talks, probably stayed there 7 to 10 days. And then it continued. Now, this is the talk that I will deliver. This is, I just retired from my services last March. I don't know about the Europe. In the USA, there is no notion of retirement, but in India, we retire at the age 65, which I attended last March. So he is my last student, the first author. You see the Anandarup Roy. In this, I guided probably more than 20 students in this, Shubho being the first. Shubho Mitra was my first PhD student. Probably he's the first PhD in cryptography in India. I think he did 99 or around 2000. So now in this work, we had some collaborators. One is my friend from Japan, Professor Sakurai. And the other one, after she finished her PhD, she started looking into this problem also. But meanwhile, she moved to Holland. She became a postdoc of Bert student, other Bert, in this university. So Shuprita happens to be now my student's wife also, because they were doing PhD in the same in my group only. So they also joined a little part. I don't know how much I can go in this work. Let me see how much I can proceed. At least try to point out the issues that he has tried to tackle. So first, let me get into the very basic of secret sharing. And normally what I do, I don't even look at my slides when I talk. The slides are only to guide me what to speak. So this is the classical Shamir's secret sharing. Probably all of you know, but still just to refresh. So you have a secret. And this is a threshold scheme, meaning that you define a threshold K, that you have a number of participants, so small n. And then the secret will be shared amongst these n participants, so that any K or more participants, if they come together with their shares, they can compute the original share. And any group of participants less than K number, they will not be able to find out. So that was his concept and how he realized it. So he would have a K minus 1 degree polynomial, if K is the threshold. And the constant term A0 is going to be the secret. And I think the dealer or somebody, the super user, he or she will choose other k minus 1 random numbers from a given Galois field and form a polynomial. And then you choose publicly, if you are n participants, some n values from that field and compute the polynomial on those n values. This n values are public. Okay, then when you compute the or evaluate the polynomial or those n points, you get n different values. And naturally, if from one value you cannot get back. If I choose x, then from px you cannot compute what is x. So those px1, px2, etc., I may call s1, s2, sn are given to these participants. And since this polynomial of degree k minus 1, if k of them come out with their shares and their corresponding x is public anyway, you can actually form French linear equations with k variables and k equations, k or more. And easy to see that the corresponding matrix is going to be Van Ormond, so non-singular, as long as the inputs were distinct. So you can solve for all these coefficients, and as a result for this particular my secret also. Okay, but then came, the researchers have to generalize things because we have to move on and we have to think different kind of applications. I think in my last talk I gave one application where we were talking about how you use the metroid theory in constructing these schemes. Because this is only a threshold scheme. If I want to make it more general, well, the general problem is still hard. We don't know what the solution. So general problem is that I define a set of participants and I define a class of subsets of those set of participants. Any class. I call it access structure. And a secret is going to be shared amongst all these participants in such a way that if this subset is a member of my access structure, from their share, you can compute the original secret back, or their superset, that's obvious. And if it's not if you come up with some members of these different participants who are not member of the access structure, you cannot compute the original secret. Now, this makes my access structure to be any member in the power set. Now, this general problem, as of today, is not proven to be NP hard, but is believed to be hard, like factoring or discrete log. So what you do, we try to get into some kind of special access structure and see if we can solve the problem. So I think in my other talk, I used that if access structure has certain properties that inherit from metroids, then we can certainly do something good. We can do this p-time algorithms. But that's very limited scope. But anyway, you have to work on, if you see any paper on the secret sharing, people will try to identify, well, to the best of your mathematical ease, identify access structure and try to solve problem for that access structure. And that's how the research goes on. Hoping that someday we can solve the general problem, because it's not proven to be NP hard. So we do have some hope. Some student somewhere may be the revolutionary and come up with a general solution. And we are waiting for that day. So this is, okay. So this is the Shamir scheme. Now we'll talk about a little more generalization. I think I was inspired by Stinson. Stinson happened to be my senior at Waterloo. So when I entered as a PhD student there, Doug was completing his thesis. And we had the same advisor. So just like I had a meeting, I attended a meeting today with Ingrid and her co-research students. So I used to sit in that meeting. So I came to know Doug pretty well with our coffees and meetings and team meetings. But so he, along with his, he was retired. In Canada, you're not supposed to retire, but he retired. Doug retired, I think, a couple of years back. He said, 65 years, good enough for me. Now I can rest. So he was trying to introduce problems like, in secret sharing, two things. Number one, if, this is kind of a complementary problem. If a participant loses his or her share, can some other participants help him or her to reconstruct his or her share? This is one. And just a complementary problem, could there be another subset of participants from whose share they could frame this participant? So suppose this 8 are there, they are participants, and is it possible that these 3 of them, from their share, they can compute the share of him? Then they can easily frame this person. The other problem is, he has lost his share. Can some subset of, say, these 3 or these 4 can help him in reconstructing the share? Because normally the delay is gone. Once the thing is set up, the delay is actually gone, where the delay is no more in the picture. So these 2 are complementary problems introduced, and they gave a different, they used Shamir's scheme, but in a bit more combinatorial way. And they introduced something called distribution design. So I give an example before going to the formal definition. So if you see, they start with a 5-9 scheme of Shamir. That means there are 9 participants, and the threshold is 5. So you need 5 of them to come together with their shares so that they can reconstruct the secret, and 4 or less, they cannot. So what they did here, so you take something called a design. So this means that you compute, say 9 participants. So this is just some identifier for the participants, 1, 2, 3, 4, 5, 6, 7, 8, 9. So to each of them, we have a public value from the Galois field, x, on which we evaluate the polynomial. We call it S1, S2, blah, 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 S9. Now, what Stinson and his team recommends that we don't just give S1 to 1, S2 to 1, S3 to 1, and so on and so forth. Instead, we give them a set of S. Okay, so for example, in this one, so now they will have 12 participants. The number changes, 12 participants, and the first participant is given the share of 1, 2, and 3. Okay. Second participant, they give the share of 4, 5, and 6. So now everybody is given 3 values of those S. For the S, we had chosen some random numbers, some 9 numbers from the Galois field, and we evaluated them on those ones, and those are the shares. But here we give 3 values of the S. So 3 shares of the original one. Now this one I call the share of 1. Now I have got more participants, actually 12. This could be 9 also. This could be more. Doesn't matter, so I could stop here at 9 also. But with the property that if you look at any 2 of them, and union, say if you take B1 and say B6, if you take the union, they will have 5 values, 5 different shares. But sometimes it's 6, say B1 and B2, you have 6. But you take any 2 of them, and if you take union of them, they will have 5 members, or 5 those shares. And then since the threshold was 5 the other time, so any 2 of them, if they come out with their shares, now they can actually compute the original share back, because they have 5 values. So this becomes different. Now the threshold becomes 2. Original one was threshold 5, number of participants 9. Now in this one, threshold is 2, and number of participants up to 12. We could stop here also, we could stop here also, up to 12. But here they can actually do some combinatorial computation and handle those concepts of reconstructing one's share or framing somebody. Now, if it so happened that 2 of them any two of them, their union include these ones. This means these two can actually frame. So if 1, 2, 3 could be a subset of the union of any two of them, then these two could frame this person. But here it's obvious because it has got 3 shares. I can always get 3 of them, one with having 1, one having 2, one having 3, and those 3 can always frame it. But if you see here, no 2 of them can frame it. Because you take any 2 of them, make them union, and it's not going to cover a third person. So this is what they call frame proof. And this is introduced by Evu Desmet, this frame proofness. So this helps in both the sides. If somebody says, for example, here if 1, 2, 3, he loses 1, 2, 3, then you could get other members who could actually give you 1, 2, 3. And you want from minimum number of people. So the problem there becomes minimum number of people who can come together and help this guy in recovering his or her share. And frame proof, I want that with, well, many of them can always frame, but at least a threshold that this many of the participants cannot frame a different participant. So these two are basically go side by side, and people have done much of work. Now, what we do here, this new concept came. Yes?
Just a question. So once you say that we want to reconstruct the shares of the last time guy that lost the keys, so why we cannot use just a standard reconstruction approach like the Lagrange interpolation? You just want to copy the shares but not reconstruct with Lagrange interpolation?
No, because yes, no, what you tell is true, but even this might be lost. He doesn't even know that he's 1, 2, 3.
Or he doesn't know even his indexes?
Yeah, he may not even know his indexes.
How you can find the people that they have the same indexes?
So we have to try out a few possibilities, and that's not too many possibilities, and we can possibly give that person. We have to work out some possibilities. Okay, so there's some little commentary there. But it may swap. But right, if I know the indexes, then I can compute because the x values are public. No, what I doesn't know right, that's not possible because the polynomial is not public.
Yeah, my point is that in Shami's secret sharing, we just defined ourselves the main secret point 0, but the secret could be defined any other point. So if you have lost your shares, so any qualified set would allow you to reconstruct the points that you want. So it doesn't mean to be point 0, it can be any point.
Yes, that's true.
The question is that if the qualified set is 2, because each party has 3 shares,
Mm-hmm.
so we need just 5 shares to reconstruct. So we need to find a friend. Maybe the only reason is that because of efficiency. Because if you want to reconstruct, you have to...
No. One is the other is that because the person has no access to the polynomials.
Yeah, that's true, but I don't talk about the polynomials. If you have the points of the polynomials, you can interpolate by Lagrange interpolation. If you know that it's taken...
Oh yes. You're right. But I think they are talking also of the case where this index also he might lose, and then they're having some combinatorial method to even recover the index. Okay, so we can talk. So I think Doug, they were talking about even losing the indexes. Okay, so then came the next notion, which is basically the part of our research. They defined something called a ramp scheme. Okay, what's the ramp scheme? So I have got, this is wrong. This should be small theta. So I have got, I'm distributing secrets and amongst L many participants, and I've got 2 parameters, small theta and capital theta. This should be small theta. Okay, this means if there are small theta or less number of participants come with their shares, they cannot compute the original secret back. Okay? Well, capital theta, which is typically larger than small theta, if that many participants come together, and they can compute the share back. Okay, but in between, they cannot get the share exactly, but they can get partial information about the share. So there is a gray line somewhere here. And if the small theta is just capital theta minus 1, then that's as good as the threshold scheme. Okay, so I have got a capital theta, small theta, this is greater than this, say 2 and 4. In that case, 4 of them can reconstruct the share, 2 or less cannot, but 3 of them can get some partial information. And the example they gave when they introduced this problem, or maybe I can just add, there's chalk, so I can just add a small example here. These things are, so suppose I've got, I want to have a 2, 4. Small theta is 2 and capital theta is 4. So what I do, for some funny reason, by the way they described, the share is in 2 parts, S0 and S1. So maybe A0 and A1. Okay, maybe S0 and S1. Okay, then we have a polynomial so S0, S1 is at the part of the secret, and A1, A2 are random numbers from that field, third-degree polynomial. Okay, and we compute in 4 defined points, say 1, 2, 3, 4, and those are my PXs. Give it to these people. If 4 of them come together, they can actually form 4 equations in 4 unknowns, and they can solve S0, S1, A1, A2. Now, if 3 of them come together, we'll have 3 equations in 4 unknowns. And you can eliminate A1 and A2. First year algebra. So we'll have a linear relationship between S0 and S1. This is a partial information about my secret. But if I have two equations, then I cannot eliminate both A1 and A2 to get a relationship between S0 and S1. Always a random number will come. So they have no information at all. From 2 equations, whatever I do, I cannot eliminate both the random numbers, A1 and A2. Okay? So clear? So this is A2, 4, and they give a general definition with this L and theta. So this is general definition. So using this Shamir scheme, they show that, well, this is possible to have these RAM schemes. And it seems RAM schemes are in use, in practical use. That's what these authors mention. Now we are going to work, but this RAM scheme basically talks about a threshold like this, and say less than. So what we are trying to think about different kinds of RAM scheme, maybe a bit more general class, and we'll define our RAM scheme differently. Well, less than that you cannot, more than that you cannot. But if you are within that RAM limit, what you want to do that some subsets of that size may be able to reconstruct, but not all of them. So if it is 2 this side, 4 this side, 3 is my that fuzzy part. So some 3 members may be able to recover, but not all. So that's how we are trying to define our RAM scheme. So what we did, okay, so this is what, okay, so what we did, maybe I come here later on. So I'll tell our result, that what we got here. So this is this tensor product or the Cartesian product. So we are looking into, if we look into combinatorics, the basic thing is our, what you call the BIBD. Hope you understand. So BIBDs are points and blocks having certain properties. So if we have two BIBDs, V1, K1, lambda 1. So V1 is the number of points, K1 is the size of the block, lambda 1 is the number of times each pair occurs, B1 is the number of blocks, and R1 is the number of times each point appears in number of blocks. If you have these two of them, okay, then we can actually get a tau 1 B1 expandable scheme, what Stinson defined. In fact, the one he got is actually comes from a BIBD. That's actually the affine plane. So we can get this one, and then we suitably modify this B by some translation, and then what you can get, if you do this Cartesian product, then you have a ramp scheme where small theta is this tau 1 minus 1 times tau 2 minus 1 plus 1. I'll give the example later on. And the capital theta is tau 1 minus 1 times B2 plus 1, tau 2 minus 1 times B1 plus 1, and their minimum. And the number of participants is B1 times B2. So in this case, let me just go to the example. Okay. So here I have got one BIBD. So there are 4 blocks, there are 4 treatments, each one has got 3 elements. So this is actually an expandable scheme from Shamir. And this is another one, 5, 4, 3 BIBD, very trivial BIBDs. So 5 participants. Now if I do this, if I modify this little bit, and then if you do the Cartesian product, what you get here, from here we get a 2-4 expandable scheme using this previous method. Because any two of them, if you look at any two of them, if they're union, they will have all the 4. Because there are, in the original one, the threshold was 4. You need 4 of them to reconstruct this one. Now, if you take, now what I'm doing here, I'm giving participant 1 3 shares, participant these 3 shares, take union of any two of them, this will cover all the 4. You take any two of them, say this one and this one, I have got 1, 2, 3, 4. Okay, here you take any two of them, you will find their union will have all the 5. You take this one and this one, 1, 2, 3, 4, 5. Take this one and this one, 2, 3, 4, 5, 1. So any two of them will have all the 5. Because this is a property of my BIBD. So what I'm going to have here are 4 participants, here are 5 participants. If I take the tensor product or the Cartesian product, I will have 20 participants, 4 times 5. And what we're having here, so what was my previous formula? So tau 1, tau 2 both are 2 here. So this is my small theta is 2 minus 1 times 2 minus 1 plus 1, which is 2. And this is, my B2 is 5. Tau 1, tau 2 are 2. So this is 5 plus 1, 6. And this is 4 times 1 plus 1, 5. So minimum is 5. So what we have here, but after all these things, okay, so what we have here, we have got a 20 participants, a new scheme. I have increased the number of participants to 20. And then ramp 2 and 5, say any 5 of them can compute the secret. 2 or less cannot. For 3 and 4, well, certain subsets can, certain subsets cannot. So this is the ramp scheme, and I think this was and this we can generalize. So this general scheme was probably the first general ramp scheme. We didn't see any other general ramp scheme before that. So if I give you an example here, okay, so this was ultimately my So these are my 20 participants and what all shares they are going to get. Again, the function of the index, not really the share value. Okay, here we find that any collection of 5 players or 5 or more can reconstruct. Such 2 or less cannot. 3 and to 4 this may be able to some sub-collection, not all. But what was important here, I could see that P2 and P6 could reconstruct a frame P1. So what we constructed here, rather poor, because some 2 of them can frame a person. That's not quite acceptable. So what we did, we modified this scheme a little bit, and then we made it a frame proof. So we did some work on that we did not need all that information. Here we could actually exclude some information, but yet essentially we could compute it back. We threw them out and made sure that 2 of them, this P2 and P6, and no 2 of them could actually frame. So this is actually frame proof of 2. No, so 3 of them could frame, but no 2 of them could frame. So this was okay. Now came some different concepts like verifiable secret sharing scheme. See, this happens in multiparty computation all the time if a player becomes dishonest. So can we handle that? So what will happen if a player becomes dishonest? He or she will give wrong shares. Ultimately, the group will compute a wrong secret. Now, can you prevent that? Okay, so this is what is called, I think this was introduced by, I'll see the reference, verifiable secret sharing scheme. This is one important thing. And then there is other concept called, let me see. Okay. Another concept is, can we hide the access structure? But not everybody knows the access structure, because that makes certain attacks possible. Now, well, the people should be happy to get their shares and the method of computation. Now, do they have to know access structure? See, it's no longer maybe a threshold scheme. So can I hide the access structure and still do it? So these 2 things came into picture. So what we did, for implementing this one, what we have done, we have started defining an access structure, tokens. So each member, along with their share, will also give them a token. And we have given a method of generating the tokens. We have used certain kind of randomization in generating this thing, because that will help us in giving certain proofs. Randomize it appropriately, and the tokens are given. So from the tokens, so now, if any group of people want to reconstruct the share, they will first exchange their tokens, not the actual values. Okay? Okay, and from there we'll make a decision whether they can actually reconstruct the shares or not. These tokens are going to be used for verifiability purpose. They don't first exchange the actual shares. And then we have certain theorems, certain concepts here, which I'll just define here. Okay. So we give certain notions of what is perfect completeness. So if I have a authorized collection of parties such that this is greater than the capital theta, identify itself as a member of the access structure, that means this probability should be 1. Because I've introduced some randomization while generating the token. But I'm putting some properties on that generation of these tokens. So the first thing is that if the way we have got it, that if you are a valid subset, then the tokens will identify you with probability 1. But if we're not a valid one, so this is between theta and theta, then we cannot identify with probability 1, but we identify with probability 1 minus epsilon 1, so given epsilon 1. So this is our notion of perfect completeness and epsilon 1 completeness. And these are the properties we are insisting on generating these tokens. Then we define some other concept like perfect soundness. Now if we have these unauthorized ones, then the probability that we have defined this function, that we can identify them unauthorized with probability 1. And for RAM collection, which is between this and 2, we can almost always identify that this is outside. Because I know that for certain subset I can, for certain I cannot. So if you are not qualified, we'll identify them with probability 1. But some of these ones which are, we may fail with a very low probability of epsilon 2. So this is what we introduce, epsilon 2 soundness. For the qualified one, we want perfect. For the ramp ones, we have given a notion of this epsilon 2 soundness. Okay, and what is statistical hiding? Because we are trying to get rid of the access structure from the being public, and the notion is that these tokens that we have, these are generated from access structure gamma on access structure gamma prime. This difference is very small. That means we cannot guess which access structure is giving us these tokens. So we are giving this notion of statistical hiding, that these probabilities are very close. Okay, and we give again for the ramp ones, we have given for RAM collection, we have a defined notion that this we could show actually equal to a given epsilon. This is less than some given epsilon. We could not achieve really exact epsilon. So with these notions, we are telling that if you want to define a RAM scheme, you have to also define certain algorithms, certain methods, and they should satisfy these properties. These are all very abstract mathematical probability properties. You must attain these things. And the scheme that we have constructed, it does satisfy all these properties. Okay, so the tensor designs that we have designed from, so we basically started from 2 BIBDs, okay, which gives the Stinson's notion of distributing designs. Okay, and we need this because if you have to do this frameproofness or verifiability, etc., we need this kind of stuff. And then this algorithm of tensor products with certain modification, with certain mathematical properties, we have shown that this is we can actually have an access structure hiding one, and it's also verifiable. So we first work on this token. So we have an algorithm for token generation. It involves a lot of randomization so that these probability properties are achieved. You know, I think I'll stop here because if you're interested, the computations are very mathematical, long computations. I don't want to put it. I can share the paper. Just finish the paper, I can share the paper, how the proofs go. But these are the concepts that we have tried to introduce for RAM schemes. So secret sharing scheme, this can, less than that they cannot. General problem, we don't know the solution. So they come with a notion called RAM scheme. They cannot, they can, in between, they may recover, they know something. Some of them know something. Okay, and then we introduce certain, we didn't introduce, people have introduced verifiability, frameproofness, then access structure hiding to make it more secured. And we have given a formal definition of these concepts in terms of those probabilities and those epsilons and etc. And we have shown, we have designed one scheme using those tensor products which satisfy all these properties. Okay, the proofs are very long and very clumsy. So if you're interested, I can send you the paper. Okay, any